Okay, so good morning. So let's begin our real analysis 2 class. So it's paper coded MDH 453 real analysis 2. Analysis 2. So now unit 1 is Riemann so it is Stieltjes integral. So little bit difficult to pronounce this word. Okay, so the first definition: let closed interval a comma b be a given interval in real line R. So by a partition P of closed interval a comma b, we mean a finite set there is nothing but this P of points of this closed interval a comma b of the form P is equal to x0, x1 and so on up to xn, such that this x0 is nothing but a, that is a is equal to x0 comma x, and less than a1, this is less than as x1, less than x2, less than so on up to less than xn minus 1, less than xn, and xn is nothing but this point b. So partition is nothing but we are taking some points from closed interval a comma b, some n points in an increasing order. Okay, so let's see the next definition. So this definition says, okay, let f be a bounded function. Let f be a bounded function on closed interval a comma b in real line. Okay, then there exists then there is real numbers, then there is real numbers, or then there exist real numbers small m and capital M, such that using this bounded there exist real numbers m and m such that m is less than or equal to f of x, which is less than or equal to capital M for all x belongs to closed interval a comma b. So for any partition P, so this is the continuation of this definition. So for any partition, so now you know what is partition. For any partition P, say it's equal to x0, x1 and so on up to xn. For any partition P is equal to x0, x1 so on up to xn of closed interval a comma b. So we put delta xi is nothing but xi minus 1 for all I 1 less than or equal to I less than or equal to n, and okay, now let's explain with respect to a geometrical interpretation. So let's draw a curve. So say this is x-axis and this is y-axis, and this is y-axis, and consider a curve. Say some yes, let's take this. Okay, let's draw a curve. So okay, in the beginning of our introduction we have taken f of f is an non-negative function. So for timing it is not assume that it is this is just a function. So yeah, it is now it is looking like a non-negative function. Okay, let's try to draw this non-negative function. Yeah, this is some now f of x. This is now f of x. This is the point A, and this is the point B. This is the point B. Point B. Okay. Now the partition is red. So the partition B. This is now x1. So this is x0. This is x1, and this is x2, x3. Say somewhere I have some xt, and say this is okay. So xn minus 1. And this is xn. Okay, this is the partition. So delta xi means it's the difference, it's the length of the, we can say the smaller intervals. Okay. And mi is nothing but infimum of f of x, where this x lies between xi minus 1 and xi. So say somewhere I have, say let's write this. Okay. Yeah. Say this is xi and this is xi plus 1. Now just draw this. Yeah. So mi means consider all the function value between xi and f of xi minus xi plus 1 and take the infimum. So it is somewhere this will be now your small mi. Okay, now say, and capital mi is nothing but supremum of f of x in the interval xi minus 1 and xi. Okay, so, it is not. So it's x is between xi minus 1 and xi. So there is a small correction now. Let's say it's xi minus 1 and this is xi. This is xi. Okay, xi minus 1, xi minus 1. This is mi, and in this figure it now capital Mi is nothing but this point. It's a small mi, it's a capital Mi. Okay, now. And so we put L, P, F, and we are calculating this for all I 1 less than or equal to I less than or equal to n, and this is also for all I less than or equal to 1. ಅಂದರೆ ಈ ಪ್ರತಿ ಇಂಟರ್ವಲ್ ಅಲ್ಲಿ ಕೂಡ ಇದನ್ನು ನಾನು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತಾ ಇದ್ದೇನೆ. ನೆಕ್ಸ್ಟ್ wait a second. This LPF, it is LPF. It's nothing but summation I is equal to 1 to n mi delta xi. Now what is this? See, ಇಲ್ಲಿ ನನಗೆ ಏನು mi small mi ಸಿಗ್ತದೆ, ಈ ಸ್ಮಾಲ್ mi ಸಿಗ್ತದೆ, ಅದಕ್ಕೆ ಈ ಡಿಫರೆನ್ಸ್ ಅನ್ನು ಮಲ್ಟಿಪ್ಲೈ ಮಾಡಿದಾಗ ನನಗೆ ಏನು ಸಿಗ್ತದೆ, ಈ ಏರಿಯಾ ನನಗೆ ಸಿಗ್ತದೆ. ಎಸ್, ಸೊ ಇಲ್ಲಿ ನನಗೆ m1 ಏನು ಸಿಗ್ತದೆ, ಸ್ಮಾಲ್ m1. ಇಲ್ಲಿ ವಾಟ್ಸ್ ದ ಸ್ಮಾಲೆಸ್ಟ್ ವ್ಯಾಲ್ಯೂ, ಸಮಥಿಂಗ್ ಲೈಕ್ ದಿಸ್. ಸೊ ದಿಸ್ ಏರಿಯಾ. ನಾವು ಇಲ್ಲಿ ನನಗೆ ಸ್ಮಾಲೆಸ್ಟ್ ವ್ಯಾಲ್ಯೂ ಯಾವುದು, ಸೇ ಸಮಥಿಂಗ್, ಸೊ ದಿಸ್ ಇಸ್ ಸ್ಮಾಲೆಸ್ಟ್ value. So I will get this area. So ಪ್ರತಿ ಈ ಸ್ಮಾಲರ್ ರೆಕ್ಟಾಂಗಲ್ಸ್ ಗಳು ಸಿಗ್ತದೆ, ಅದರೆಲ್ಲ ಏರಿಯಾವನ್ನು ಕೂಡಿಸಿದಾಗ ಸಿಕ್ಕಿದ ಏರಿಯಾಗಳನ್ನೆಲ್ಲ ಒಟ್ಟು ಮಾಡಿ ಬರ್ತದೆ LPF. Similarly, and UPF is nothing but summation I is equal to 1 to n capital Mi delta xi, capital Mi delta xi. Now see again in this see, yeah, see here it is m1 is nothing but this, so with respect to this, and m1 into and m1 the function value and this length into this length, so you will get the area of this bigger rectangle. Now here it is something like this, so again you will get, so here it is this, so you will get this entire area, this entire, yeah. So adding areas of these higher rectangles or larger rectangles, so I will name it as UPF. Okay, now if you observe m and these mi's, see m is the smallest value of f, because it's a bound between bound of f and less, which is we can say it's infimum of f over closed interval a comma b, and m is the supremum of f over closed interval a comma b. Now so we can say this small m is less than or equal to mi, and if you observe in this figure also mi and small m and capital A are the infimum and supremum of function in a small interval. So we can say this small mi is less than or equal to capital Mi, and this capital Mi is again less than or equal to your capital M, because it's an entire closed interval a comma b. So for all I between 1 and n. Now thus m into b minus a, which is nothing but m into, so this b minus a is nothing but the length of this this interval. So I can write this length in terms of by adding all this length, that is, what is this length? That is x1 minus x0. What is that? It is delta x1. It is delta x2 minus x2 is x2 minus x1 is nothing but delta x2. x3 minus x2 is nothing but delta x3. So using this I can write as m is equal to summation m into summation delta xi, where I is from 1 to n. Now this is nothing but, so summation I is equal to 1 to n m into delta xi. Now if you observe from this inequality, I can say this one is less than or equal to summation I is equal to 1 to n small. Instead of this we can write the small mi is less than or equal to small mi into delta xi. Again the small mi is less than or equal to capital Mi, so it is less than or equal to summation capital Mi into delta xi. I is from 1 to n and to n. Again this one is less than or equal to summation I is equal to 1 to n capital M into delta xi. Okay, now I can take this m outside, so it is m into summation I is equal to 1 to n delta xi. So this is what m into, what is now this is again the length of the interval, it is b minus c. So my this sums here to sum into mi delta xi and capital Mi delta xi. It lies between small m into b minus a and capital M into b minus a. And what is this? There are some bounds again. Okay, let's move forward. It is okay. Yeah. We define the lower Riemann integral, of f with respect to x over closed interval a comma b by, so we define lower Riemann integral of f with respect to x over closed interval a comma b by we denote it by integral a to b, and here it's a line. So this will this is not a minus a, this represents a lower Riemann integral of f with respect to x, that is f dx which is equal to supremum of LPF, where supremum is taken over, where supremum is taken over all partitions of closed interval a comma b. So ನನಗೆ ಇಲ್ಲಿ ಇಲ್ಲಿ ನೋಡಿ, ಇಲ್ಲಿ ಈ ಸಮ್ ಹೇಗೆ ಬರ್ತಿದ್ದೇನೆ, ಇದು ಇಲ್ಲಿ ಕೊಟ್ಟ ಒಂದು ಪಾರ್ಟಿಷನ್ ಈ ಸಮ್ ಬರ್ತಿದ್ದೇನೆ. ಹಾಗೆ ಪಾರ್ಟಿಷನ್ ಅನ್ನು ನಾನು ಚೇಂಜ್ ಮಾಡ್ತಾ ಅಂದ್ರೆ ಈ ಕ್ಲೋಸ್ ಇಂಟರ್ವಲ್ ಆಗುವ ಎಲ್ಲ ಪಾಸಿಬಲ್ ಪಾರ್ಟಿಷನ್ ಗೆ ನಾನು LPF ಅನ್ನು ಫೈಂಡ್ ಮಾಡಿ ನಂತರ ಅದರ ಸುಪ್ರೀಮಮ್ ತಗೊಂಡ್ರೆ ನನಗೆ ಲೋವರ್ ರಿಮನ್ ಸಿಗ್ತದೆ. ಅಂಡ್ ಲೆಟ್ಸ್ ಸಿ ವಾಟ್ ಇಟ್ ಈಸ್. ಈಗ ನೋಡಿ, ಈಗ ಜಸ್ಟ್ ಬೈ ಇನ್ಕ್ರೀಸಿಂಗ್ ದ ನಂಬರ್ in this of elements in this partition, ಈ ಪಾರ್ಟಿಷನ್ ನಂಬರ್ ಗಳನ್ನು ಜಾಸ್ತಿ ಮಾಡ್ತಾ ಹೋದಾಗ ನನಗೆ ಏನಾಗ್ತದೆ, ನನಗೆ ಇಲ್ಲಿ ಈಗ ಇನ್ನು ಚಿಕ್ಕ ಚಿಕ್ಕ ರೆಕ್ಟಾಂಗಲ್ಗಳು ಸಿಗ್ತಾ ಹೋಗ್ತದೆ, ರೆಕ್ಟಾಂಗಲ್ಗಳು ಸಿಗ್ತಾ ಹೋಗ್ತದೆ. ಸೊ ಅವುಗಳ ಏರಿಯಾವನ್ನು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತಾ ಹೋದಾಗೆ ನನ್ನ ಸಮ್ ಏನಾಗ್ತದೆ, ನನ್ನ ಸಿಗುವ ಸಮ್ ಅದು ಈ ಕರ್ವಿನ ಏರಿಯಾಕ್ಕೆ ಹತ್ರ ಆಗ್ತಾ ಹೋಗ್ತದೆ. ಅಂಡ್ ಇಲ್ಲಿ ನನಗೆ ಸಿಗುವ ಎಲ್ಲಾ ಪಾರ್ಟಿಷನ್ ಗಳಿಗೆ ಎಲ್ಲಾ ಏರಿಯಾವನ್ನು ಫೈಂಡ್ ಮಾಡಿದಾಗ ಆ ಏರಿಯಾಗಳ ಸುಪ್ರೀಮಮ್ ಅನ್ನು ತೆಗೆದಾಗ ಅದು ಈ ಕರ್ವಿನ ಇದಕ್ಕೆ ತುಂಬಾ ಹತ್ರ ಆಗ್ತಾ ಹೋಗ್ತದೆ. ಓಕೆ, this is the idea. Similarly we define upper Riemann integral of f with respect to x over closed interval a comma b by it is integral a to b. Here it's a line, so this will again indicate the upper Riemann integral. F dx is nothing but now we are taking infimum of UPF. Let's see. ಇಲ್ಲಿ ನಾನು ಈಗ ವಾಪಸ್ ಇಲ್ಲಿ ಅಪ್ಪರ್ ಸಮ್ ತಗೊಳ್ಳುವಾಗ ನನಗೆ ಮೇಲಿನಿಂದ ರೆಕ್ಟಾಂಗಲ್ ಅನ್ನು ಡ್ರಾ ಮಾಡ್ತೇನೆ. ಹಾಗೆ ನಂಬರ್ ಅನ್ನು ಜಾಸ್ತಿ ಮಾಡಿದಾಗ ಈ ಮೇಲಿನಿಂದ ಡ್ರಾ ಮಾಡಿದ ರೆಕ್ಟಾಂಗಲ್ ಅವುಗಳ ಏರಿಯಾ ಈ ಕರ್ವಿಗೆ ಈಕ್ವಲ್ ಆಗ್ತಾ ಹೋಗ್ತದೆ. ಆಗ ನಾನು ಏನ್ ತಗೊಳ್ತೇನೆ, ಐ ಆಮ್ ಟೇಕಿಂಗ್ infimum and that is upper Riemann integral, that is known as upper Riemann integral of f. So we define okay, sorry, if this lower Riemann integral a to b f dx is equal to the upper Riemann integral a to b f dx, then f is said to be Riemann integral over to be Riemann integrable over closed interval a comma b, and we write f belongs to script r, so over closed interval a comma b. So if you see somewhere f belongs to this, then the meaning is f is Riemann integrable. Okay, now let's move forward. The common value of this two, that is lower Riemann integral is equal to upper Riemann integral. Now they are equal, and that equal quantity is denoted by integral a to b f dx, and we call it as Riemann integral. Of f with respect to x over closed interval a comma b. Riemann integral of f with respect to x over closed interval a comma b. Okay. Now see a Riemann lemma. Some lower Riemann integral need not be equal to upper Riemann integral always. That means there is some function which is not Riemann integrable. That is, there is some function which is not Riemann integrable, and this was given by mathematician Riemann's guide, his PhD guide Dirichlet. Dirichlet is also one of the greatest mathematician. So mathematician. Okay. The problem is so suppose f is a mapping. Suppose f is a mapping from f is a mapping from closed interval 0, 1 to R given by f of x is equal to 0 if x is irrational, and it's 1 if x is rational. Then with this Riemann approach, it is fails to identify the Riemann integral of f. So let's see how. So for any partition, p is equal to x0, x1, so on up to xn of closed interval 0, 1. If you take mi, it is a infimum of f of x between xi minus 1 less than or equal to xi, and this is always equal to 0, because see, function value is 0 if x is rational, and it is 1 if x is irrational. Function value is 1 if x is rational, 0 if x is irrational. Now if you take any smaller interval, there is rationals and irrationals. So function value, what is the infimum of those function values in any small interval? It is 0. Similarly, if you take the capital Mi, which is nothing but supremum of f of x in between xi minus 1 and xi, again this is nothing but 1, because functions value between any interval is either 0 or 1, and because there are in any interval, if you take any smaller interval, there is rational and irrational, hence the supremum is 1 in that interval. So therefore if you calculate LPF, it is nothing but summation small mi delta xi. Now small mi is 0, so this one is 0, this one is 0. Now UPF is nothing but summation, so it's is equal to 1 to n, so it is from 1 to n capital Mi delta xi. Now capital Mi is 1 for all I between 1 and n. Therefore this is nothing but summation I is equal to 1 to n delta xi. Now what is this? It is nothing but length of this interval, and what is the length of this interval? It is 1. Now take any partition, this one is true. So supremum of this, that is supremum of LPF is nothing but 0, and what is this? It is nothing but lower Riemann sum 0 to 1 f dx. And what is upper Riemann sum? It is 0 to 1 f dx is nothing but infimum of UPF, and it is nothing but here we are getting it as 1. So lower Riemann sum is not equal to upper Riemann sum, hence this function is not Riemann integrable. Okay, so let's move forward. Now let's see a generalized form of Riemann integral. Actually Riemann integral, so there's a generalized form. It's given by one of Dutch mathematician. Forgot his full name. It's ending with this, how to pronounce it? It is something Stieltjes. Okay, so it's Riemann Stieltjes integral. Next one is the Riemann Stieltjes integral. So Riemann integral is one of the special case of Riemann Stieltjes integral. Now what it is? Okay, let's see this. So again you are considering again the same thing, that's f is a bounded f be a bounded function. So I'm repeating all the things. That's f is a bounded function on closed interval a comma b in the real line. Then there exist then there exist real numbers m and m such that m is less than or equal to f of x, which is less than or equal to m for all x belongs to closed interval a comma b. And okay, now introducing one more term uh, with Riemann integral, that is we are introducing a new term, that is let alpha be a monotonically increasing function. Monotonically increasing function on closed interval a comma b, closed interval a comma b. So what do you mean by monotonically increasing function? That is, if x is less than y, implies f alpha of x is less than or equal to alpha of y. Okay, so it's a monotonically increasing function. Then also alpha is bounded monotonically increasing function, because if you take any point between, say it's defined on closed interval a comma b, so if you take any point between a, this implies a is less than or equal to x less than or equal to beta b, which implies alpha of a is less than or equal to alpha of x, which is less than or equal to alpha of b. This will says your alpha is bounded function. Now consider a partition of closed interval a comma b. P is a partition of closed interval a comma b. Say x naught x1 so on up to xn of closed interval a comma b. Again consider your small mi. Small mi is nothing but infimum of f of x as these are all same thing, and capital Mi is nothing but supremum of f of x, where x is lies between xi minus 1 and xi. You have to calculate this for all I between 1 and n. Now also put L. So now finding the LP. In the previous part we denoted by LPF. So here it is LPF comma alpha, and we are writing the summation is from 1 to n to mi into delta. It is not delta xi, it is now delta alpha I. Then what is this delta alpha I? So delta alpha I is from this partition, that is we are writing delta alpha is nothing but alpha of xi minus alpha of xi minus 1. In the previous part delta xi was xi minus 1, so here it is alpha of xi minus alpha of xi minus 1 for all I between 1 and n. So now if you observe delta xi delta alpha is always greater than equal to 0, because your alpha is monotonically increasing. So let's move forward, and you are writing UPF alpha is nothing but it is summation I is equal to 1 to n capital Mi delta alpha I. In a similar way. Okay, moreover here also your m is less than or equal to small mi, which is less than or equal to capital Mi, which is less than or equal to capital M for all I between 1 and n. And you can also observe m into alpha of b minus alpha of a, that is nothing but m into summation delta alpha I is equal to 1 to n. And the previous it was delta xi, so this is nothing but summation I is equal to 1 to n, so it is m into delta alpha I. So now again m is less than or equal to mi, so it is less than or equal to summation I is equal to 1 to n mi into delta alpha I. Again it is less than or equal to summation I is equal to 1 to n, mi is less than or equal to capital mi into delta alpha I, again it is less than or equal to summation I is equal to 1 to n into m into delta alpha I. You can take m is outside, so this you will get summation I is equal to 1 to n delta alpha I, and which is nothing but m into alpha of b minus alpha of a. That is your these two sums is lies between m into alpha of b minus alpha of a and capital M of m into alpha of b minus alpha of a. Now we are defining, as we defined lower sum and upper sum in the previous we are defining lower, we define lower Riemann Stieltjes integral of f with respect to alpha over closed interval a comma b. So in the previous it was with respect to x over closed interval a comma b. Here we are writing with respect to alpha over closed interval a comma b by integral a to b. Again here it is line to represent is a lower Riemann Stieltjes integral of f. So here we are writing f d, not f into dx, we are writing it f into d alpha, which is nothing but supremum of L P F alpha and upper Riemann Stieltjes integral of f with respect to alpha over closed interval a comma b by integral a to b. So it's to this line will represent upper Riemann Stieltjes integral f d alpha into infimum of UPF alpha. Now if these two integrals are equal, that is lower Riemann Stieltjes integral of f with respect to alpha over closed interval a comma b is equal to upper Riemann Stieltjes integral of f with respect to alpha over closed interval a comma b, then we say that f is Riemann Stieltjes integral over closed interval a comma b with respect to alpha over closed interval a comma b, and in this case we write f belongs to R of alpha, and in this case we write f belongs to R of alpha. And the common value between these two is denoted by a common value of these two, that is wait a second, common value, it is nothing but integral a to b f d alpha. It is called as Riemann Stieltjes integral of f with respect to alpha over closed interval a comma b, over the closed interval a comma b. Okay. So now if you see, if you observe what is the geometrical interpretation of introducing alpha. So let's see first now this. If you take alpha of x, alpha is a monotonically increasing function. If you take alpha of x is equal to x, you are getting the same, that is integral a to b f d alpha of x. So if I write f of x d alpha of x, then this is nothing but integral a to b f dx. So we are getting, if I take f of alpha of x is equal to x, then I'm getting Riemann integral of f, Riemann integral of f. So then why this? So the thing is, if you observe, alpha is a mapping from closed interval a comma b to alpha of A comma alpha of B, because your alpha is monotonically increasing function. So your Riemann integration is over closed interval a comma b with respect to x. Say this is closed interval a comma b. Say this is now alpha of a and alpha of b. So this function will scales your closed interval a comma b, or in other words the speed of approaching from A to B is changed. ಇನ್ನೊಂದು ರೀತಿಯಿಂದ ಹೇಳಬೇಕಂದ್ರೆ ಈಗ ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಬರುವ ಸ್ಪೀಡ್ ಅನ್ನು ಒಂದು ರೀತಿಯಿಂದ ಕಂಟ್ರೋಲ್ ಮಾಡುವಂಥದ್ದು ಆಲ್ಫಾ ಆಫ್ ಎಕ್ಸ್ ಇಂದ ಆಲ್ಫಾ ಆಫ್ ಎ ಇಂದ ಆಲ್ಫಾ ಆಫ್ ಬಿ ಗೆ. ಲೈಕ್ ಸೇ ಈಗ ಈ ಒಂದು ಎ ಅಂತ ಹೇಳುವ ಜಾಗದಿಂದ ಬಿ ಅಂತ ಹೇಳುವ ಜಾಗಕ್ಕೆ ಹೋಗ್ಬೇಕು, ಟ್ರಾವೆಲ್ ಮಾಡಬೇಕು. ಸೊ ಸಪೋಸ್ ನಾನು ಈಗ ಹೇಗೆ ಟ್ರಾವೆಲ್ ಮಾಡ್ತಿದ್ದೇನೆ ಅಂತ ಹೇಳಿದ್ರೆ ಬಸ್ ಟ್ರಾವೆಲ್ ಮಾಡ್ತೇನೆ. ದ ಬಸ್ ಇಸ್ ನಾವು ಆಲ್ಫಾ ಇಸ್ ನಾವು ಬಸ್. ಸೊ ಈ ಬಸ್ಗೆ ಹೋದಾಗ ನಾನು ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಹೇಗೆ ಹೋಗ್ತೇನೆ? ನಾನು ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ನಡ್ಕೊಂಡು ಹೇಗೆ ಹೋಗ್ತೇನೆ, ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಬಸ್ಸಲ್ಲಿ ಹೇಗೆ ಹೋಗ್ತೇನೆ. ಸೊ ದ ಸ್ಪೀಡ್ ಇಸ್ ಚೇಂಜ್ಡ್. ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಹೋಗುವಾಗ ಬಸ್ಸಿನ ಸ್ಪೀಡ್ ಅಲ್ಲಿ ಹೋಗ್ತೇನೆ. ಸೊ ಸೇ ಬಸ್ ಫಾರ್ ಒಂದು ಜಸ್ಟ್ ಎಕ್ಸಾಂಪಲ್ ಕೊಡ್ತೇವೆ ಅರ್ಥ ಮಾಡಿಸೋಸ್ಕರ. ಬಸ್ ಹೀಗೆ ಹೋಗ್ತಾ ಇದೆ, ಅಲ್ಲಿ ನಿಂತಿದ್ದು, ಇಲ್ಲಿಂದ ವಾಪಸ್ ಹೋಗ್ತಾ ಇದೆ, ಸ್ವಲ್ಪ ಹೊತ್ತಲ್ಲಿ ನಿಂತಿದ್ದು ಹೋಗ್ತಾ ಇದೆ. ಸೊ ಇಲ್ಲಿ ಹೋಗುವಾಗ ನಿಮ್ಮ ಒಂದು ಗ್ರಾಫ್ ಹೀಗಿದ್ರೆ ಇದನ್ನು ಇನ್ನು ಹೇಳಿದಾಗುತ್ತೆ, ಸ್ಟ್ರೆಚ್ ಮಾಡಿದಾಗುತ್ತದೆ. ಸೊ ಏರಿಯಾ ಬದಲಾವಣೆ ಆಗುದಿಲ್ಲ, ಏರಿಯಾದಲ್ಲಿ ಬದಲಾವಣೆ ಆಗುದಿಲ್ಲ. ನಾನು ಹೋಗ್ತಾ ಇರುವ ಸ್ಪೀಡ್ ಅನ್ನು ನಾನು ನೋಡ್ತಾ ಇರುವುದು, ಸ್ಪೀಡ್ ಅನ್ನು ನಾನು ಅಬ್ಸರ್ವ್ ಮಾಡ್ತಾ ಇರೋದು. ಸೊ ಇಲ್ಲಿ ಎಕ್ಸ್ ಎಕ್ಸ್ ಈಗ ಎ ಗೋಸ್ ಟು ಎ ಅಥವಾ ಎ ಗೋಸ್ ಟು ಎ, ಲೈಕ್ 0 ಗೋಸ್ ಟು 0, 1 ಗೋಸ್ ಟು 1 ಆತರ ಕಾನ್ಸ್ಟೆಂಟ್ ಫಂಕ್ಷನ್ ತಗೊಂಡಾಗ, ಕಾನ್ಸ್ಟೆಂಟ್ ಅಲ್ಲ ಐಡೆಂಟಿಟಿ ಫಂಕ್ಷನ್ ತಗೊಂಡಾಗ ಯಾವುದೇ ಬದಲಾವಣೆ ಇಲ್ಲ. ಅಂದ್ರೆ ಸ್ವಲ್ಪ ವೇರಿಯೇಷನ್, ಸಮಥಿಂಗ್ ಲೈಕ್ ಸೇ ಒಂದು ಪಾಯಿಂಟ್ ಇಂದ ಇನ್ನೊಂದು ಪಾಯಿಂಟ್ ಹೋಗ್ತಿದ್ದೇನೆ. ದಿಸ್ ವಾಸ್ ಮೈ ಸ್ಪೀಡ್. ಸೊ ಐ ಆಮ್ ಟೇಕಿಂಗ್ ಅ ಸ್ಪೀಡ್ ಆಫ್ x ಸ್ಕ್ವೇರ್ ಸಮ್ x ಕ್ಯೂಬ್. ಸೊ ಓಕೆ, ಇದನ್ನು ಹೇಳೋದಕ್ಕಿಂತ observe from this is x goes to x square x cube. ಅಂದ್ರೆ ನಾನು ಅದನ್ನು ಚೇಂಜ್ ಮಾಡ್ತಿದ್ದೇನೆ. ಸೊ some monotonically increasing function. Okay, so this is the Riemann Stieltjes integral. Okay, let's move forward. So you have seen what is a partition. So if P is partition, if P is a partition, it's a partition of closed interval a comma b. If a partition of closed interval a comma b, and P star is again is as another partition. If P star is another partition, is another partition of closed interval a comma b. P on the partition, P star another partition. If we say P star is refinement of P if P is contained in P star. P star ಅನ್ನು ಯಾವಾಗ ರಿಫೈನ್ಮೆಂಟ್ ಅಂತ ಹೇಳಿ ಹೇಳಿದ್ರೆ P ಅದರ P ಅಲ್ಲಿರುವ ಎಲ್ಲ ಪಾಯಿಂಟ್ಗಳು P star ಅಲ್ಲಿ ಇದ್ದಾಗ, ಅಂದ್ರೆ P star ಅಂದ್ರೆ ಏನಾಯ್ತು? It's partition which contains the points of P and some more points of P star, some more other points, more than that. ಒಂದು ಅದೇ ಆಗಿರ್ಬೋದು ಅಥವಾ ಅದಕ್ಕಿಂತ ಜಾಸ್ತಿ ಆಗಿರ್ಬೋದು. So P star is a points of partition of closed interval a comma b which contains some more points of P. So then we say P star is a refinement of P. So if again some observation, if P1 and P2 are two partition of closed interval a comma b, then P1 union P2 is also partition of closed interval a comma b. Moreover, you know that P1 is contained in this, similarly P2 is contained in this. So we can say this P1 union P2 is a refinement of P1 as well as a refinement of P2. Okay, so let's see one result. theorem. So let f be a bounded real valued function defined on closed interval a comma b. Let f be a bounded closed interval a comma b, defined a bounded real valued function defined on a closed interval a comma b if p star is a refinement of p star is a refinement of p of closed interval a comma b. If p star is a partition, p is a partition, so there p star is a refinement of p of closed interval a comma b, then the first thing is L p f alpha is less than or equal to L p star f alpha. The first thing. Okay, so this is nothing but say this is a curve, and with respect to p I have a partition, and I have a lower Riemann sum. Okay, now so ಈಗ ನಾನು ಇದಕ್ಕೆ ನಾನೀಗ ಈ ಪಾರ್ಟಿಷನ್ ಇನ್ಕ್ರೀಸ್ ಮಾಡಿದಾಗ ಏನಾಗ್ತದೆ, ಪಾರ್ಟಿಷನ್ ಇನ್ಕ್ರೀಸ್ ಮಾಡಿದಾಗ ಇನ್ನೂ ಸ್ವಲ್ಪ ಏರಿಯಾ ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ಸಿಗ್ತದೆ, ಅಥವಾ ನನ್ನ ಏರಿಯಾ ಈ ಕರ್ವ್ನ ಏರಿಯಾಕ್ಕೆ ಇನ್ನೂ ಹತ್ರ ಆಗ್ತದೆ. ಅದು ಹಾಗೆ ಹತ್ರ ಆಗುದು ಅಂತ ಹೇಳಿದ್ರೆ ನಾನು ಪ್ರೀವಿಯಸ್ ಆಗಿ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿದ ರೆಕ್ಟಾಂಗಲ್ ಏರಿಯಾಗಿಂತ ಈಗ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿದ ರೆಕ್ಟಾಂಗಲ್ ಏರಿಯಾ ಜಾಸ್ತಿ ಆಯಿತು. ಪಾಯಿಂಟ್ಸ್ ಆಡ್ ಮಾಡಿದಾಗೆ ರೆಕ್ಟಾಂಗಲ್ಗಳ ಏರಿಯಾಗಳು ಕೂಡ ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಯ್ತು. So this one, so we shall first do this. So let p is equal to x naught, x1 and so on up to xn be a partition of closed interval a comma b, the partition of closed interval a comma b. Then let p star is a refinement of p, that means p is contained in p star. P is a refinement of p star is a refinement of p, means p is contained in p star. Suppose p star, so that means there are some points of there are more there are in p star contains points of p and some more points of closed interval a comma b. So suppose p star contains just one point more than p, just 1 point more than p. So let me denote this point by, say, x star is that extra point which lies in p star, and when it is lies in p star, so it must be between some 2 points of p, lies between 2 points of p. Say so x star is a point in p star, then this p x star will lies between, say, xj and xj plus 1, let's say xj minus 1 and xj. It will not equal to xj minus 1 or xj because x star is not in p. Okay, now with respect to my p, what is mj? Mj is nothing but infimum of f of x, where x between xj minus 1 and xj. Infimum of f of x, where x between xj minus 1 and xj. This is with respect to p. Now with respect to p star, I have partition, say, x1 so on up to x2 and so on up to xj, and x star and xj minus 1. Let me write properly. Okay, that's right. So I have partition x1, yes, x0, x1 and so on up to xj minus 1, x star, xj and so on up to xn. Yeah, this is my partition p star. So now so mj with respect to this p. Now so there is also this small this will represent an largest smallest value in this interval. So now let's find what's the smallest value in this interval. That is, so let me denote it by w1. Small w1 is nothing but infimum of f of x, where this x lies between, it is xj minus 1 and x star. And w2, small w2 is nothing but again infimum of f of x, which is between x is between x star less than or equal to xj. X star is like x between x star and xj. Now say curve is something like this. Okay, this is xj minus 1 and say this is xj, and I have x star. This partition is in p star. Now in say ಇಲ್ಲಿ ಬಾಕಿರುವ partition. So if I find, so if I find right L P F alpha. Now you know what it is. It is nothing but it is so you have seen it is nothing but summation small mi delta xi delta alpha in demonstrated. So now ಇಲ್ಲಿ ಪ್ರತಿ ಈಗ ನಾನು p star ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತಿದ್ದೆ. ಪ್ರತಿ ಇದರಲ್ಲಿ ಇಂಟರ್ವಲ್ ಅಲ್ಲಿ mi ಗಳನ್ನು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿ ಅದಕ್ಕೆ ಈ ಡೆಲ್ಟಾ ಆಲ್ಫಾ ಇಂದ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡ್ತೇನೆ. ಸೊ ನನಗೆ ಇಲ್ಲಿ ಏನು ಸಿಗ್ತದೆ, ನನಗೆ okay, it's something m1 delta x1 plus so on. So somewhere I will get these two, that is w1, so delta alpha 1, delta alpha 1. So this this difference, so with this replace with alpha, that is that alpha of x star minus alpha of xj minus 1 plus w2 of alpha of xj minus alpha of x star and the remaining thing. So if I find lp star f alpha minus lp f alpha, now ಇದು ಕೂಡ ಸಿಮಿಲರ್ಲಿ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೇವೆ. ಆದ್ರೆ ಇದಕ್ಕೂ ಇದಕ್ಕೆ ಏನ್ ಡಿಫರೆನ್ಸ್, ನನಗೆ ಇಲ್ಲಿ ಎಲ್ಲ ಪ್ರತಿ ಫಸ್ಟ್ ಟರ್ಮ್ ಇದ್ರದ್ದು ಸೇಮ್ ಇರುತ್ತೆ, ಸೆಕೆಂಡ್ ಟರ್ಮ್ ಸೇಮ್ ಇರುತ್ತೆ. ನನಗೆ ಈ ಟರ್ಮಿಗೆ ಬರುವಾಗ, ದಟ್ ಇಸ್ ಈ ಇಂಟರ್ವಲ್ಗೆ ಬರುವಾಗ, ಇಲ್ಲಿ ಒಂದು ಪಿ ಸ್ಟಾರ್ ಅಲ್ಲಿ ಒಂದು ಎಲಿಮೆಂಟ್ ಜಾಸ್ತಿ ಇರುವ ಕಾರಣ ನನಗೆ ಎಲ್ಲ ಕ್ಯಾನ್ಸಲ್ ಆಗಿ ಇದು ಮಾತ್ರ ಉಳಿತದೆ. w1 alpha of x star minus alpha of xj minus 1 plus w2 of alpha of xj minus alpha of x star and idraddu that one, that is nothing but minus mj into alpha of xj minus alpha of xj minus 1. So now just by solving, that is take this as w1 as it is, alpha of x star minus alpha of xj minus 1 now plus w2 of alpha of xj minus alpha of x star minus mj into alpha of xj. So in this I am adding and subtracting alpha star, so it is minus alpha of x star. Now last term as it is, that is alpha of xj minus 1. Now combining the common term, so it is nothing but now alpha of x star minus alpha of xj minus 1. So this is nothing but now w1 minus mj into alpha of x star minus alpha of xj minus 1 plus here it is again, it is w2 minus mj into alpha of xj minus alpha of x star. Now observe from here, mj is the smallest value in this interval, and and W1 is the smallest value in this interval, and W2 is the smallest value in this interval. So if by observing this we can say W1 and W2 are always less than or equal to Mj. Therefore this one is greater than 0, this one is also greater than 0. Is it correct? Sorry, I'm making a mistake. So Mj is less than or equal to W1 and W2. Mj is the smallest value in a larger interval. So Mj is always less than or equal to W1 and W2. Now alpha is monotonically increasing, and your xj minus 1 less than x star, which is less than xj. Therefore alpha of x star minus alpha of xj minus this one is also greater than 0, greater than or equal to, it's greater than 0. Similarly alpha of xj minus alpha of x star is also greater than 0. Therefore all of this term is greater than or equal to 0. That means this difference is greater than or equal to 0. That is LP star f alpha is greater than is equal to LP f alpha. Hence the result. So similarly prove that UP alpha is greater than or equal to UP star f alpha. Prove that UP f alpha is greater than or equal to UP star f alpha. This one is left as an exercise. Thank you.